Okay, hello. Our last video was about how to pick good names for functions, and that is an extremely important element, as the last video went through, on making sure that your program is intelligible, maintainable, usable, all sorts of good things. But in this video, we're going to talk a bit more about the other parts of functions, namely the function signature, i.e. the parameters and the types of the parameters that are used to call the function, and the underlying thing on the computer in the programs the computer executes that relate to the functions that you programmed. Now, I'm going to say this talk is going to be mainly given in terms of C and C++. Everything I talk about relates to Fortran or Rust or any other compiled language that you like. It doesn't really have a lot in common with Python because, as we mentioned in a previous video, Python to a very great degree is effectively running its own software on its own virtual CPU to a great degree, its own virtual processor, and so it doesn't really have to follow any of the rules that normal programs do. So I'm going to just write an incredibly simple C program that uses a single function. Okay, so it's going to be a simple function that takes a single integer parameter and returns nothing, and just prints the value of my integer that I passed it. Okay, very simple. I'm going to create the main entry point as well. And I'm just going to call that with 1, 2, 3, 4 as a test integer. Now, if I compile that, it compiles and it runs and it produces 1, 2, 3, 4. So it does exactly what I expect. Now, if I look at this, you might be tempted to think that, well, what actually happens? Because bear in mind that behind the scenes, what the compiler does is produce a series of instructions that the CPU can actually run directly. The instructions are just handed to the processor, and the processor runs them. So what you might think is that behind the scenes, this test 1, 2, 3, 4 is implemented by simply taking my content here and putting it into the program where I called my function test with this I parameter replaced by 1, 2, 3, 4. Now that does happen. Compilers very definitely do that. It is called inlining, and it is a very important speed optimization that compilers make. But they make it pretty much only for speed. Calling a function in the other way that I'm about to talk about carries a bit of a performance penalty. I won't really go into that now, though it's something we'll probably cover in a later video, but it does carry a performance penalty. And so you can take the code, put it in place, avoid that performance penalty, and save a bit of time, make your code a tiny bit faster. But it's worth pointing out that it is only worth doing that for very small functions that don't take very long to run. Now, this function is easily short enough that it would benefit from that, but when I compile it again to show you something, I'm going to compile it with all optimizations off, so it won't do that inlining. And the problem is, of course, if you take the content of a big function and paste it in everywhere the function is used, your program gets a lot bigger. What you in fact want from the perspective of not winding up with a massively large program is exactly the same thing as you have here. You have a little piece of code that gets reused. And that's exactly what happens. Inside the program, there is a section of the program code where you just say, jump to this point in the code and execute the instructions that you find there. Now, the parameters are passed through something called a stack frame, and that's partly what covers the, or partly what causes that cost of calling a function. But as I say, we'll come to that later. But the key thing about it is that section of code inside the program on pretty much all modern computers isn't simply an offset. The program doesn't just have programmed in, go to memory location 68259 or whatever, and execute those commands. It does it using something called a symbol. And a symbol represents a place in the program, the compiled executable program, that it should go to. And if I compile this again with no optimizations to make sure it's there, I can run this through a tool called nm. My program is called a.out, and I run nm on that, and this is a list of all of the symbols that are in that program. Now there's quite a lot of them, and they do a lot of things. Some of them, for example, this one, glibc225, that's saying that's in the system glibc library. But here is the one that looks very familiar, test. Okay, it's called test. That could be a coincidence, but it isn't. If I go in here and rename this function not test, but something that would never come up randomly, I'm going to use the traditional word for this sort of thing of wibble, and put that in. My code still compiles, my code still runs, but now if I run that nm program again, I now have a symbol called wibble. So essentially, all that the compiler is doing is it is taking the name of my function and saying, okay, here is a symbol saying this is a point of the program to jump to, it's actually this number here, if you want to run the program, the function, subroutine, whatever you want to call it, wibble. Okay, fair enough. That's the job done in C. Now, when you get to other languages, things get a bit cleverer. So I'm now going to create something in C++ instead. Okay, so I'm now going to create two functions with the same name, and they're going to be basically the same. They look a bit different because I'm not going to use a C printf command, but they're going to be a bit similar. I'm going to go back to calling them test, and one of them is going to take an int, and print it, and the other one is going to take a float. And actually, I'm going to make a change here so you can see which one gets used. Okay, so these are just print commands again. If you're not so familiar with C++, they probably look a bit weird, but they are just print. Put space in there. Okay. Okay, now I'm going to create my main program again. I seem to keep saying maint today. It isn't even a word. And I'm now going to do test of 1, 2, 3, 4. And then I'm going to do test of 1, 2, 3, 4.0. Okay, and I'm going to compile that one with G++. Oops. You will notice that my original tests.c program compiled as well. That wasn't what I meant to do, but most of C is a subset of C++, so a simple program like that will compile fine with a C++ compiler. Call of overload is ambiguous. Okay. Perhaps I shouldn't have used an int and a float. Yeah. I shouldn't. Oh, of course. So I complicated things. I forgot. All decimal numbers in C++ are double precision floating point numbers, 64-bit. I've created here something using a 32-bit floating point number. So I'll come back later to why it was complaining about that being ambiguous. Okay, so that now compiles, and if I run it, it's called the separate functions for the separate types. Now this is called function overloading. And if I go back in here, you'll see the functions have the same name. They just take different parameters. Now what's happening behind the scenes is when you call the function, the compiler knows the type of this thing on the right-hand side, and it calls the function that matches that type. Now, the reason I completely accidentally showed you that error earlier is because the rules for how it selects the right function are actually quite complicated. So here, where I've got an int and an actual float, this f on the end means treat this number as a float, not a double. The rules are very simple. It just goes find the function that matches that exactly. On the other hand, when I didn't have that f, this was a double precision number. And because there isn't a function that exactly matches it, it has to go, okay, I have to convert that number into something, either into an integer to call this function or a floating point number to call this one. And the rules say it can't choose between those two, so it complained and wasn't willing to compile. So this is a very important thing that pretty much all modern languages other than C have now, which is you can do this function overloading, where you can have a single function that takes different types and it will select the right one. And there is always this complexity involved in doing that, with making sure that the compiler is able to unambiguously select the right function for the type you give it. Now, we will at some point have a video describing that actually in detail, but for the moment, for this video, let's just let it suffice to say that it's quite complicated. And while this function overloading is brilliant and allows you to do a lot of things that would be a major headache without it, it can also introduce new and slightly hard to interpret errors. But another question comes up, which is, with that names of these functions being the same, how does that symbol thing work? If a symbol uniquely identifies a place in the code, you can't have a unique identifier that is the same twice. And the answer to that is something that in C++ and in most other languages that do this as well is called namemangling. And you'll be able to see that if I compile that again with O0 to make absolutely sure everything's there. If I run a.out through, you see I have here functions that have the word test in the name, but they include now this underscore z4 test f and underscore z4 test I. So let's ignore the underscore z4 completely for the moment. That's a fairly messy thing about exactly what the compiler is doing. But essentially it's taken the type and combined, the name of my function, and combined it with the type of the parameter. Here just f for float and I for int. Well, that's fairly easy to see, but that really is all it is. So this is once again a sort of inside the black box. It looks as though it's doing something extremely clever, but in a sense it's not actually that clever at all how it does it. It just combines bits of information it has to create these unique symbols, and then it just chooses the right one based on the information it already has while trying to call the function. Because it's worth pointing out, of course, it has to know the types before it calls a function in a language like C, C++, Fortran, etc. Simply because otherwise it wouldn't be able to give you the error messages if you try and call a function with the wrong type. So all that it does here is it selects from several candidate functions and picks the one that matches. Now, I will say that these names are unhelpful in a lot of senses, and there is a tool that you can use to demangle the name, and you can either do it with nm, you literally just put in demangle, and now that is telling me rather more helpfully that there is a test float and a test int, because nm here just knows how the names were mangled to get to this point, and it can undo them again. And you'll see that some of the other really quite obscure ones here, zn sol zf at glibc, whatever, become something that if you're a C++ programmer looks a lot more normal, as in standard O-stream operator double arrow. So that's my print statement. So that's basically showing how that works. And you can go even further with C++, and it does much the same thing. So I'm now going to copy my test C++ program, create a new one, and I'm going to show what in many senses is the most powerful feature of C++ compared to the other languages that are common in academic use at the moment, which is the templating system. So C++'s templating system is basically a mechanism by which you can say, I'm not going to have to write out these functions for different types manually. I want to just say, for any type, do this. Now, because it's worth pointing out, these tricks that you see C++ doing here, lots of other languages can do as well. Taking Fortran as an example of what a lot of people think is an old language, Fortran has function overloads. It doesn't do it the same as this. You don't give the function the same name. You give each version of the function a different name and put in an interface block to say, connect these together under a single name, but it's the same idea. And Fortran uses namemangling as well. The fact that you can have the same function in two different Fortran modules, and the symbols don't collide there, is because it name-mangles combining the name of the module and the name of the function, and those do have to be unique in a single program when combined. But anyway, back to C++. So if I take just my one test function, I'll delete the second one, and I will now put in my template. Okay, so that template is now saying, I want to make this function a template, i.e. I want the compiler to produce a function for any type, and the type I want it to produce is this thing, TID. So essentially everywhere that I said before int, I get rid of it and replace it with TID. Now, here in this string, you can't do that. There is no truly standard way of getting the name of a type in C++ like this. You can get something that's maybe sort of like it, but you can't guarantee that it's there or that it's different, and you certainly can't guarantee that it's human readable. So I'm just going to get rid of that. But okay, I'm now going to do that, and I'm now going to put in a third test, which is going to be not a numeric type of any kind, but a string. Okay, test hello world, and I compile that. It compiles, and it runs, and it prints my integer, it prints my float, and it prints my string, hello world. In a language like Fortran, I would have had to write at least 2 different functions for that. And realistically, if I wanted this integer to not become converted to some kind of floating point number, I'd have had to write 3. So this is the really nice, really powerful thing in C++. By using this templating system, you can create functions for different types automatically. And in a sense, this becomes a bit more like languages like Python, because I can put anything in this function so long as every type I try and call the function with can do those things. So if I have 2 types that can be added, I can just use add. If I have 2 types that can be subtracted, I can use subtract. I can do whatever. So I will also state that while this is, in a lot of senses, the most common usage of the type system, and certainly the most common use that I've seen in academic code, the templating system is actually extraordinarily powerful in C++, to the point that it can easily become very confusing as well. But for the moment, just think of the templating system as producing a function. And the question then comes, is that what it's actually doing? Well, at that point, we can go back to our friend nm. Compile it with O0 again. I will say there is a very good possibility those functions hadn't been inlined. I'm just doing the optimize level 0 to be as sure as I can be. And I'm now going to run nm over that. And here we go. We have 3 versions of test. Now the names are not just the same. You have an F and an I, which looks pretty familiar. But then you have this EVT underscore at the end here, and these capital I's, and it all looks like a bit of a mess. But the idea is behind the scenes exactly the same. It looks as though the templating system is doing something tremendously clever to make things work with different types. But it really isn't. It's literally just, as the code is compiled, effectively taking your code and going, okay, everywhere I have underscore TID, replace it with int, because I called it with an int. Everywhere it says TID, replace it with a float, because I called it with a float. And then those become distinct types out here. If I called it again with a double precision number rather than a float, there'd be a fourth one. And once again, I will, just to demonstrate it, show that if you demangle, you get, once again, a fairly human-readable function name. You get here test. These triangular brackets, as I pretty much as I use them in there, that's the templating thing. That's that extra bit of code at the end. And of course, yes, it's a constant pointer to a character, that string literal I sent, not a standard string, which makes it actually a lot shorter than it otherwise would have been. But basically, that's sort of it. So this has been briefly going through sort of 3 black boxes and showing what they're doing. So first of all, the idea of symbols inside the program. You just have these symbols that show the program when it's running. Jump here and execute these to this part of memory and execute these instructions. Function overloading. In a sense, not a black box. You write every function, but behind the scenes, it really is just producing the 2 functions, separate symbols. And templates, which are really pretty much the same as function overloading in terms of the final result, but it's just that the compiler generates those functions for you rather than you having to write them manually. And you can see here from this dump from NM that that's exactly what it's done. And this really is the great power of C++ over a lot of other languages. It's power that comes with quite a lot of costs as well. Sometimes doing things with the templating system can be very difficult, but it is a lot of additional power for certain types of problem. So next week we will be back again with a different video, and I will finish this one here.